Okay, kids, I'm going to go through the Castlelearning and the main ones that you guys got wrong. Anything under a 70, I'm going to go over. So this one's pretty straightforward. Well, kind of. It says compared to Jupiter and Saturn, Venus and Mars have greater what? Well, if you remember, Jovian planets are large, gassy, farther away from the sun, right? Low density, made of hydrogen and helium. And the terrestrial planets, right? Venus and Mars are small, rocky, dense, closer to the sun. So you're looking through these answers, you don't really see any of those. And also remember, double check on page 15, bottom page 15, it gives you those data, right? It gives you that data right here. Mercury, Venus, Earth, Mars, it has that data. It will show these small, rocky, and dense, close to the sun. Jupiter, Saturn, Uranus, large, right? Gaseous, low density, farther away from the sun. But you don't really see an answer for that for this guy. But if you remember, these guys are closer to the sun, they're going to have faster orbital velocities, the things that are closer to the sun, right? Mercury is moving the fastest around its orbit, then Venus, right, all the way out to Pluto, which has a orbital, this revolution takes 248 years. So the answer is orbital velocities because Venus and Mars are closer to the sun. So we're going to go down over here to number 2 here. So compared to the other groups of stars, the group that has a relatively low luminosity and low surface temperature is the what? Reference tables. Page 15 again. We're going to go up to this guy, right? And we're going to say, all right, well, luminosity is low. It's got to be down here. It's got to have low temperature. If you remember, on the x-axis, it's inverse. It starts at 30,000. It does not start at 0. I don't know why they do that. They just did it. You have to talk to Hertzberg or Russell about why it's inverse on the bottom. But if you go over here, low luminosity, low temperature, that is in the red right here. So it's a red dwarf would be the answer. All right, let's look at this guy. So if we're looking down here, so for the comet, as it goes around its orbit right here, we have the tail. It points away from the sun. It doesn't go behind it, right? So if you're looking, it's not like when you're running down the street and you had like a cape on, the cape would flap behind you. That's not necessarily true. The tail of the comet points away from the sun. So even though the sun is going this way right here, the comet's tail is pointing that way. So in this case, it's pointing that way. That would be the answer. It's pointing away from the sun, right? And let's look at this last guy right here, right? We have F1, F2, two foci, right? And if you remember, the formula for eccentricity is E equals D over L. Eccentricity equals distance between the foci over the length of the major axis. You don't have to remember that because it's on your reference tables. And all you got to do is you take a ruler over here, measure between focus 1, focus 2, get a number. Measure the length between this guy and this guy, get a number. You divide the distance between the foci by the length of the major axis, and it has to be less than 1. It needs to be 0 point something. And if you did that, you should have got about 0.7, which is the answer to this guy. If you pick the one that says 1.4, you know it's wrong off the bat. You can cross that off because it has a 1 in front of it, right? It's got to be 0 point something. So those are the main ones you guys got wrong. And that closes out our astronomy. So good job, guys. And that is it.